Our cosmic map has a giant blank spot we cannot see past. This is the Zone of Avoidance, a vast region of the sky where our view of the distant universe is completely blocked by the Milky Way's own thick clouds of dust and stars. It is a permanent blind spot in our vision, a curtain drawn across nearly 20% of the heavens. Behind that curtain lie some of the universe's greatest secrets, from hidden superclusters that pull entire galaxies to dark matter clues that could redefine physics. By the end of this journey, you will know 25 astonishing facts about what hides in this cosmic void and why it matters to everything we think we understand. We will uncover how an invisible force is tugging at our galaxy and what monstrous structures might be lurking in the shadows. What do you believe is waiting for us in the dark? The very heart of our own galaxy is what keeps us most in the dark. This is the primary zone of avoidance, a permanent celestial fog bank created by the Milky Way's central bulge. Picture our galaxy not as a flat disk but as a fried egg with a thick, glowing yolk at its center. That yolk is the galactic bulge, a densely packed sphere of ancient stars, swirling gas, and immense clouds of fine, dark dust. It is this dust that acts as the ultimate light-blocking curtain. When astronomers point their telescopes toward this region, the light from any distant galaxy or quasar are trying to shine through is not just dimmed, it is utterly absorbed and scattered into oblivion. The sheer concentration of material is so great that it creates an impenetrable wall across a vast swath of the sky. In angular terms, this zone of avoidance spans about 30 degrees by 120 degrees, a giant, blurry smudge centered on the constellation Sagittarius. For anyone trying to map the cosmos beyond our own stellar neighborhood, this area represents the single most frustrating and significant observational barrier. It is as if we are trying to chart a continent while standing in the middle of its densest, most permanent fog. Every photon of light from the universe on the other side is stolen before it can ever reach our eyes or our instruments, leaving a profound and silent mystery in the place where our galaxy's core shines brightest. This galactic curtain is not a single, uniform blindfold. The truth is, we are navigating not one, but two major zones of avoidance split cleanly by the plane of our own galaxy. Picture the Milky Way's disk as a highway stretching across the sky, a band of faint light we call the galactic plane. Above and below this central band lie the two distinct zones, the northern and southern zones of avoidance. Their obscuring power is not equal. The southern zone, which points us directly toward the dense, dusty heart of the galaxy in Sagittarius, is by far the more challenging frontier. Here, the dust clouds are at their thickest, creating an almost total blackout for optical telescopes. Peering into this region is like trying to see through a brick wall. The northern zone, however, which looks out toward the galaxy's outer rim and beyond, is comparatively clearer. The obscuration there comes more from the sheer number of foreground stars in our own disk, which create a crowded, confusing foreground, but the dust is less concentrated. This fundamental asymmetry means our cosmic map is not just missing a piece, it is missing a piece that is far more impenetrable in one specific direction. The southern void holds the deeper secrets, and it is there that the universe's hidden architecture presses most insistently against the veil. But astronomers are not ones to be easily defeated by a cosmic curtain. Their secret weapon is light itself, just not the kind our eyes can see. To peer into the heart of the zone of avoidance, they must abandon the visible spectrum entirely and turn to the warmth of the universe. This is the domain of infrared astronomy. While the tiny grains of dust in the galactic plane are superb at blocking the short wavelengths of visible light, they are far less effective at stopping longer wavelengths, like those of infrared radiation. Think of it this way: visible light is like fine sand which gets trapped easily in a sieve. Infrared light, with its longer waves, is more like pebbles which can slip right through the same mesh. By using space telescopes like Spitzer and WISE, which are specifically designed to detect this infrared warmth, astronomers can effectively see through the dust. It is like putting on a pair of special goggles that allow you to see the heat signatures of objects hidden in a thick fog. This has revolutionized our view of our own galactic backyard. For the first time, we could map the true three-dimensional structure of the Milky Way's central bulge, seeing past the obscuring dust to understand its bar-like shape and the motions of its ancient stars. Even more thrilling, these infrared eyes have uncovered entire nurseries of newborn stars, hidden stellar factories blazing with warmth but completely invisible to optical surveys. Every glowing dot revealed in the infrared is a triumph, a piece of the cosmic map painstakingly filled in where once there was only blank space. Yet the universe whispers its secrets on many different frequencies. Beyond the warmth of infrared light lies an even more penetrating signal, a faint radio hum that slips effortlessly through the cosmic dust. This is the domain of radio astronomy, and its most powerful tool for piercing the zone of avoidance is a specific universal song, the 21-centimeter line. Every atom of neutral hydrogen gas drifting in the vastness of space naturally emits this precise radio wavelength. Since hydrogen is the fundamental building block of galaxies, this signal becomes a cosmic beacon. Crucially, those tiny dust grains that block visible light are completely transparent to these long radio waves. It is the difference between trying to see through a wall and being able to hear a conversation happening on the other side. By tuning their enormous dish antennas to listen for this specific 21-centimeter hum, astronomers can detect the presence and motion of entire galaxies completely hidden behind the Milky Way's veil. They are not seeing starlight, they are hearing the raw material of creation itself. This technique has led to monumental surveys like HIPLSS, the H.I. Parkes All-Sky Survey, which systematically scanned the southern sky. Its results were staggering, cataloging thousands of galaxies that had never appeared on any optical map. Each detection was a ghostly outline, a hidden giant revealed only by the radio echo of its most basic component. These surveys did not just fill in blank spots on the map, they revealed that the zone of avoidance was not empty at all, but teeming with a hidden population of galaxies, their silent radio whispers painting a new and crowded universe behind the impenetrable dust. Radio whispers from hidden hydrogen were the first clue to something monumental. Our entire galactic neighborhood is not drifting randomly through space, it is being pulled with immense force toward a specific point in the sky. That point lies almost directly within the southern zone of avoidance. Astronomers call this mysterious, invisible source of gravity the Great Attractor. For decades, its existence was inferred only by the strange, river-like flow of galaxies, including our own Milky Way, all moving toward a region of space that appeared optically to be nearly empty. It was as if every galaxy in our local universe was caught in a vast, slow-motion current, all drawn toward a cosmic drain we could not see. The pull was so powerful it suggested a concentration of mass equivalent to tens of thousands of Milky Ways, a gravitational anomaly of staggering proportions. Yet when we looked in that direction, our view was blocked by the very stars and dust of our galaxy's central bulge. The Great Attractor was not just a mystery, it was a hidden behemoth, its true form masked by our own cosmic backyard, forcing us to question what could possibly possess such gravity from behind the veil. That hidden river of galaxies finally has a name and a face. The core of the Great Attractor is now known to be anchored by a truly colossal structure called the Norma Cluster, a dense swarm of galaxies catalogued as a C03627. It sits about 220 million light-years away, buried so deeply within the southern zone of avoidance that it is completely invisible to optical telescopes. Yet its gravitational influence is undeniable. This is not just a random group of galaxies, it is one of the most massive and richest clusters in our entire local universe, containing thousands of individual galaxies bound together by gravity. The total mass of this cluster is staggering, equivalent to perhaps 1,000 trillion times the mass of our own Sun. Think of the Norma cluster as the dense, heavy heart of the Great Attractor system, the central gravitational anchor around which the entire mysterious flow of galaxies organizes itself. By painstakingly mapping this cluster using infrared and radio observations, astronomers have been able to calibrate a significant portion of the total pull we feel. It provides a concrete, measurable source for a large fraction of that immense force, turning a vague directional pull into a quantifiable target. Studying Norma is like finally identifying the main engine of a vast, invisible whirlpool, giving us our first real understanding of what, at least in part, is doing the pulling from behind the cosmic curtain. Even with the immense pull of the Norma cluster accounted for, the math still did not add up. The Great Attractor was not strong enough. Our galaxy and its neighbors were still moving too fast, as if something even larger was pulling us from an even greater distance. This pointed the finger of suspicion deeper into the void, toward something so immense it defied comprehension. Its name is the Shapley supercluster, the single largest concentration of matter in our entire observable cosmic neighborhood. Lying over 650 million light-years away, it is a sprawling metropolis of galaxy clusters, a gravitational titan that makes the Norma cluster look like a small town. The combined mass of all its galaxies and their attendant dark matter is almost beyond calculation. Think of it as the ultimate cosmic anchor, a supercluster of such density that its gravitational influence can be felt across hundreds of millions of light-years. While not completely hidden by the zone of avoidance, it lies skirting its very edge, its full extent partially obscured by the Milky Way's dust. For decades, astronomers debated whether the Shapley supercluster or the Great Attractor was the primary source of our motion. The emerging consensus is that we are caught in a vast cosmic tug-of-war. The Norma cluster and the Great Attractor are a significant local pull, but the distant, overwhelming gravity of the Shapley supercluster is the dominant force, setting the entire local universe into motion toward it. We are not just flowing toward a hidden drain, we are being drawn across the cosmos by the largest structure we have ever mapped. This cosmic tug-of-war between titans is written in the oldest light we can see, but to read it, we must first see through our own galactic clutter. The Zone of Avoidance presents a profound challenge to our view of the universe's very first chapter, the cosmic microwave background. This faint, all-sky glow is the cooled remnant of the Big Bang's fireball, a baby picture of the cosmos when it was just 380,000 years old. It is our single most important window into the universe's origin and evolution. But between us and that pristine ancient light lies the Milky Way, and within the Zone of Avoidance, our galaxy is not a transparent window but a brightly lit, noisy foreground. The dust and gas that obscure distant galaxies also glow brightly themselves, emitting microwaves and infrared radiation that completely swamp the delicate signal of the CMB. Imagine trying to listen to a faint, ancient symphony while standing next to a roaring waterfall. The very foreground you need to see through is drowning out the signal you desperately need to hear. For cosmologists, this means the Zone of Avoidance is not just an empty spot on a map. It is a major source of contamination that must be meticulously cleaned away. The process, called foreground subtraction, is one of the most delicate and crucial tasks in all of modern cosmology. Scientists use complex models and data from multiple wavelengths to map, and then digitally remove the emission from every speck of Milky Way dust and every wisp of galactic gas. Only then can the true, smooth background of the early universe be revealed. The complexity and density of the zone make this cleaning process especially difficult there, introducing uncertainties that ripple through our most fundamental measurements of the cosmos. In essence, to understand the universe's birth, we must first perfectly understand the messy, glowing screen our own galaxy has placed in front of it. Our struggle to see through the cosmic curtain has yielded an unexpected prize, a clearer understanding of our own galactic home. For a long time, astronomers debated the fundamental shape of the Milky Way's core. Was it a simple, symmetrical bulge of stars or something more dynamic? The answer lay hidden within the zone of avoidance itself. By using infrared telescopes to peer through the dust, scientists could finally trace the motions and positions of millions of stars in the obscured central region. What they found was not a sphere but a colossal, dense bar. Our galaxy is a barred spiral with a central structure shaped like a giant candy bar, spanning over 25,000 light-years from end to end. We are located within the disk, about halfway out from the center, and our view of this bar is edge-on, making it incredibly difficult to see directly. It is like trying to discern the shape of a football stadium while you are standing on the playing field. The zone of avoidance, ironically, became the key. Because the dust blocks our direct optical view, astronomers had to rely on the penetrating power of infrared and radio waves to map the structure. They studied the subtle, predictable motions of stars and the flows of interstellar gas, which are funneled and shaped by the bar's immense gravity. These hidden tracers revealed the bar's precise orientation, tilted about 45 degrees relative to the line between the Sun and the galactic center. This discovery was monumental. It reshaped our model of the Milky Way, revealing the central engine that drives gas toward the core, fueling star formation and influencing the orbits of billions of stars, including our own Sun. The very region that blinds us to the distant universe has become a mirror, reflecting back the true, hidden architecture of our cosmic city. This violent history of collisions is not just theory, it may be written in the stars we cannot see. The zone of avoidance could be a cosmic graveyard, littered with the ancient remains of galactic mergers. Our Milky Way did not form in peaceful isolation. Over billions of years, it has cannibalized smaller dwarf galaxies, tearing them apart with its immense gravity and absorbing their stars into its own halo. The evidence of these past feasts should be all around us in the form of faint stellar streams and disrupted globular clusters, which are the ghostly trails of stars left behind like cosmic breadcrumbs. The problem is, the thickest dust and star clouds of the galactic plane lie directly across our line of sight to the most likely places to find these relics. Imagine a crime scene where the most crucial evidence is hidden under the one rug you are not allowed to lift. Astronomers have found such streams elsewhere in the sky, like the Sagittarius dwarf stream which wraps around our galaxy. But the zone of avoidance presents a massive blind spot in this archaeological survey. If a major dwarf galaxy was torn apart on the far side of the galactic center, its entire stellar debris field could be hidden behind that curtain, completely invisible to our optical telescopes. Finding even one such stream peeking through the dust would be a monumental discovery. It would provide a missing chapter in our galaxy's autobiography, revealing the timing, direction, and scale of a past collision that helped shape the Milky Way we see today. Every hidden stream is a fossil record of a violent event, and the zone may be keeping the most important fossils of all locked away in darkness. To systematically confront this cosmic blind spot, astronomers launched a dedicated project with a disarmingly direct name, the Zone of Avoidance Galaxies Catalog. This is not a single observation, but an ongoing, multi-generational effort to build a complete census of what lies behind the veil. Its methodology is a masterclass in cosmic detective work, refusing to rely on any one wavelength of light. Instead, the ZOAG project synthesizes data from across the electromagnetic spectrum. It cross-references the penetrating warmth of infrared surveys from telescopes like WISE, the telltale radio hum of hydrogen from instruments like Parkes, and even the high-energy glare of X-rays from observatories like Chandra. Each wavelength reveals a different facet of a hidden galaxy. Infrared shows its stellar bulk, radio maps its raw hydrogen fuel, and X-rays can betray the presence of a voracious supermassive black hole at its heart. By combining these disparate clues, astronomers can confirm a galaxy's existence, estimate its distance, and begin to understand its properties, all without ever seeing its visible starlight. This painstaking process is slowly filling in the blank spaces on our map, galaxy by galaxy, reducing the profound observational bias that has always skewed our view of the universe. The catalogue is a testament to patience, proving that what we cannot see directly, we can still find by listening to its many hidden voices. Even the most violent cosmic events cannot hide their most energetic screams. While infrared and radio waves reveal the structure and fuel of hidden galaxies, they sometimes miss the furious heart beating within them. To find that, astronomers must turn to the most penetrating light of all, the searing glare of X-rays. Observatories like Chandra and XMM Newton act as our cosmic X-ray vision, and what they have uncovered behind the Zone of Avoidance is a gallery of monsters. These instruments detect active galactic nuclei, the intensely bright, compact regions at the centers of galaxies where supermassive black holes are actively feasting on surrounding matter. As gas, dust, and even entire stars spiral into the black hole's gravitational grip, they are heated to millions of degrees, creating a maelstrom of energy that blasts out high-energy X-ray radiation. This radiation has a key property. It is so energetic that it punches straight through the thick clouds of dust that block visible light. It is the difference between a flashlight being swallowed by fog and a powerful laser beam cutting right through it. When Chandra stares into the Zone of Avoidance, it does not see stars or gas. It sees the brilliant, pinpoint beacons of these feeding black holes, each one a signpost for a hidden galaxy. Every detection is a dual revelation. It confirms the existence of a galaxy we cannot see optically, and it tells us that at its core lies one of the universe's most violent and energetic processes. These hidden AGN are cosmic lighthouses, their intense X-ray beams shining through the galactic fog to guide us toward structures and motions we would otherwise never know were there. The dust clouds themselves may be hiding a deeper secret. While we map the obscuring curtain with infrared and radio waves, a significant portion of its mass could be made of something even more elusive, dark gas. This is not dark matter, but a hidden component of the ordinary interstellar medium, primarily molecular hydrogen. Under normal conditions, a cloud of hydrogen molecules is nearly invisible. It is too cold to glow in infrared, and unlike single hydrogen atoms, it does not emit the convenient 21-centimeter radio line. It simply sits there, cold and dark, absorbing starlight but giving almost nothing back. Within the dense, crowded environment of the galactic plane, especially in the Zone of Avoidance, astronomers suspect vast reservoirs of this dark gas could exist. It would weave between the dust grains we can detect, adding tremendous unseen mass to these already opaque regions. Think of a thick fog where you can only see the water droplets illuminated by a streetlight, but not the cold, heavy vapor filling the space between them. This dark gas complicates everything. It means our estimates for how much ordinary matter is locked in the galactic plane could be significantly underestimated. It also means the curtain blocking our view is even thicker and more complex than our instruments suggest, a layered veil of both seen and unseen material. Every calculation about what lies behind the zone, from the mass of hidden galaxies to the strength of gravitational pulls, must now account for this potential sea of invisible molecules, a ghostly presence within the blind spot itself. This relentless challenge has transformed the Zone of Avoidance into something more than a problem. It has become astronomy's ultimate testing ground, a laboratory for innovation where scientists are forced to invent entirely new ways of seeing. When conventional observation fails, ingenuity takes over, leading to techniques so advanced they sound like science fiction. One of the most elegant methods involves using the universe's oldest light as a universal flashlight. Scientists study subtle distortions in the cosmic microwave background, the afterglow of the Big Bang, as it passes through massive hidden structures behind the galactic plane. This phenomenon, called gravitational lensing, works because all matter, whether we can see it or not, bends the fabric of space-time. A colossal supercluster hiding in the zone will very slightly warp the path of the ancient CMB radiation streaming through it. By meticulously mapping these incredibly faint imprints, like finding the silhouette of a hidden object by studying the distortion of light on a wall behind it, cosmologists can infer the mass and location of the unseen behemoths tugging at the curtain. It is a form of cosmic shadow puppetry, where the shadows reveal the shapes of the puppets we cannot directly see. On a more direct front, powerful new eyes are staring deeper into the infrared than ever before. Telescopes like the Vista Survey telescope in Chile conduct massive, deep near-infrared sky surveys. These projects do not just glance at the zone, they stare for hundreds of hours, collecting every possible photon of warmth that manages to leak through the dust. The resulting images are not pretty pictures in the traditional sense. They are deep field data mines, revealing the faintest smudges of galaxies whose light has been reddened and dimmed by its long journey through the galactic fog. Each smudge is then analyzed, its color and brightness used to estimate a distance, slowly building a three-dimensional map of the hidden architecture. This painstaking work is complemented by another frontier, sophisticated computer modeling. Astronomers create vast, simulated universes based on our understanding of cosmology and galaxy formation. They then digitally place a virtual Milky Way, complete with a realistic zone of avoidance, in front of that simulation. By comparing what the model predicts should be hidden behind our galaxy's dust with the few clues we've gathered from infrared and radio, they can test theories and guide future observations. It is a constant dialogue between prediction and discovery, where the blank spot on the map becomes a puzzle that defines the very limits of how we explore the cosmos. This cosmic blind spot might hold the key to one of the greatest disagreements in modern science. Astronomers are locked in a fierce debate known as the Hubble tension, a stubborn discrepancy in the measured rate of the universe's expansion. On one side, we have the pristine early universe as seen in the cosmic microwave background, which gives us one very precise expansion rate. On the other side, we have measurements from nearby stars and galaxies which consistently give a faster rate. It is as if the universe started expanding at one speed but has since decided to accelerate in our local neighborhood. This tension threatens to upend our standard model of cosmology, suggesting we might be missing a fundamental ingredient in our understanding of physics. And here is where the zone of avoidance casts a long shadow. Could the discrepancy be caused not by new physics, but by something massive we have simply not seen? The local measurements rely on observing the motions and distances of galaxies relatively close to us to calibrate the expansion rate. But what if our local region of space is not typical? What if the gravitational pull from an immense, hidden supercluster, or perhaps a vast, underdense void lurking behind the Milky Way's dust is subtly tugging on these nearby galaxies, distorting their apparent motions? This would be like trying to measure the flow of a river while standing in a hidden whirlpool. Your local measurements would be thrown off by an unseen current. If such a structure exists within the zone, it could be imparting an extra velocity to our galactic neighborhood, making it seem like the universe is expanding faster here than it truly is on a cosmic average. The blank spot on our map, therefore, is not just a gap in our data, it is a potential source of systematic error in one of cosmology's most crucial measurements. Solving the Hubble tension might not require rewriting the laws of physics, but simply finally lifting the veil to see what colossal shape is pushing or pulling us from the dark. The secrets of stellar death are also locked behind this cosmic veil. While we search for hidden galaxies, the Zone of Avoidance conceals a more intimate drama playing out within the Milky Way itself. Scattered across the obscured galactic plane are countless planetary nebulae, the final, beautiful breaths of sun-like stars. When such a star exhausts its nuclear fuel, it gently puffs off its outer layers into space, creating a glowing, often intricate shell of gas. At the nebula's heart, the star's exposed core becomes a white dwarf, a hot ember that illuminates the expanding cloud. These objects are cosmic fossils, telling the story of a star's final moments and its chemical legacy. Yet within the zone, their delicate light is ravaged by the very foreground they reside in. The dust between us and them dims and reddens their glow, a process astronomers call extinction. It distorts their apparent brightness, muddies their colors, and can even hide their more intricate structures entirely. Studying them through the fog is like trying to admire a stained glass window from behind a sheet of frosted plastic. The light comes through, but the true artistry is lost. To recover that artistry, scientists once again turn to the warmth of infrared light. By observing these nebulae at wavelengths that slip past the dust, telescopes like Spitzer and Wise can see their true forms. What appears as a faint, blurry blob in visible light might be revealed in infrared as a stunning bipolar structure, with two symmetrical lobes of gas jetting from the dying star, or a complex, knotty shell shaped by magnetic fields or companion stars. More importantly, infrared spectroscopy allows astronomers to peer into the nebula's chemical soul. Every element in the expanding gas cloud emits or absorbs light at specific infrared fingerprints. By analyzing this spectral data, researchers can determine the precise cocktail of elements forged in the star's core and dredged up during its death throws carbon, nitrogen, oxygen, and even traces of heavier materials. This is forensic astronomy. The chemical makeup of a planetary nebula tells us the initial mass of the progenitor star, the efficiency of its nuclear fusion, and how it recycled its enriched material back into the galactic ecosystem. Each hidden nebula studied in the infrared adds a crucial data point to our models of stellar evolution, helping us understand not just how stars die, but how they seed the galaxy with the very elements needed for new stars, planets, and life. The Zone of Avoidance, therefore, is not only a barrier to the distant cosmos but also a dusty archive, preserving the last wills and testaments of countless stars whose final chapters we are only now beginning to read. The very heart of the darkness holds the ultimate cosmic predator. At the precise center of our Milky Way, buried deep within the densest part of the Zone of Avoidance, lies Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. Its location is the ultimate cosmic irony. The most extreme and fascinating object in our entire galaxy sits at the one spot most heavily obscured from our direct view. To study it, astronomers must peer through 25,000 light-years of the Milky Way's most crowded star fields and thickest dust lanes. Every photon of light or radio wave from that central maelstrom must run a grueling gauntlet, scattering and dimming as it fights its way toward our telescopes. Observing Sagittarius, a star, is not merely difficult, it is like trying to discern the details of a flickering candle flame through a raging blizzard. This monumental challenge demanded a revolution in observational technique. The first major breakthrough came from the silent language of radio waves. By linking radio telescopes across the globe into a virtual instrument the size of Earth, a technique called very long baseline interferometry, scientists created a dish with unprecedented resolution. This network, which would evolve into the Event Horizon Telescope, allowed them to map the intense radio emissions swirling around the black hole's event horizon. It was this very collaboration that produced the first historic image of a black hole's shadow in the galaxy M87, proving the method could pierce the cosmic static. For our own galactic center, however, even this was not enough. The dynamic, rapidly changing environment around Sagittarius, a star, required another tool, the piercing gaze of infrared light. Giant ground-based telescopes like the Keck Observatory and the Very Large Telescope employ a brilliant trick called adaptive optics. They fire a powerful laser into the atmosphere to create an artificial guide star, then use a deformable mirror that flexes hundreds of times per second to cancel out the blurring effects of Earth's turbulent air. This yields crystal-clear infrared views, allowing astronomers to track individual stars whipping around the black hole at speeds exceeding 15 million miles per hour. These stellar orbits, mapped over decades, provided the most direct and irrefutable proof of Sagittarius, a star's immense mass. It is a triumph of human ingenuity, a story of building a sharper vision to solve a puzzle placed at the most inconvenient location imaginable. Every glimpse we steal past the veil reveals not just a monster, but the intricate dance of spacetime itself, choreographed by an invisible titan we now know is there. Our most ambitious maps of the cosmos carry a permanent, built-in flaw. When massive projects like the Sloan Digital Sky Survey or the 2-Degree Field Survey set out to catalog millions of galaxies and trace the vast cosmic web, they inevitably run into a fundamental limitation, the zone of avoidance. These monumental redshift surveys, which use the stretching of a galaxy's light to measure its distance, systematically skip over the entire region obscured by the Milky Way. The result is not just a blank spot on a map, but a profound selection bias in our very understanding of the universe's large-scale structure. We have meticulously charted the distribution of galaxies across most of the sky, revealing the great walls, filaments, and immense voids that form the universe's architecture. Yet this grand map has a giant, ragged hole punched right through its center. This missing data is not a minor omission. It is like trying to understand the global climate by ignoring an entire ocean. The models we build of the cosmic web, the gravitational flows, and the overall matter distribution are all based on incomplete information. Could a major supercluster filament be passing directly behind the galactic plane, connecting structures we see on either side? Is the Great Attractor part of a wall that extends far into the zone, hidden from our view? Without the data from this missing sector, our cosmic cartography is an educated guess, potentially missing the very bridges and nodes that define the true skeleton of our local universe. To combat this, astronomers have launched dedicated, painstaking surveys focused solely on the zone itself, using infrared and radio eyes to hunt for every possible galaxy. Each new detection is a precious data point, slowly stitching the torn edges of our cosmic map back together, revealing whether the patterns we see everywhere else continue into the darkness or if something entirely unexpected lies in wait behind the curtain. Even the stars themselves can be shot like bullets from the galactic core. The dense, chaotic heart of the Milky Way, much of which is shrouded within the zone of avoidance, is not just a place of formation but also a cosmic slingshot. Here, in the crowded stellar metropolis surrounding the supermassive black hole, stars can be hurled across the galaxy at unimaginable speeds. These are hypervelocity stars, and they represent some of the most dramatic escapees in the cosmos. The mechanism is a gravitational ballet of extreme precision and violence. When a binary star system, two stars orbiting each other, ventures too close to Sagittarius, a star, the black hole's immense gravity can tear the pair apart. One star is captured into a tight orbit, while the other is flung away at speeds exceeding 1,000,000 miles per hour, fast enough to completely escape the galaxy's gravitational grip. It is a stellar version of a catapult, using the black hole's energy to launch a star on a one-way trip into the intergalactic void. But the dense star clusters of the galactic bulge offer another launch mechanism. In these crowded neighborhoods, close gravitational encounters between stars can act like a complex pinball machine, with one star getting a tremendous speed boost at the expense of others. The zone of avoidance complicates their story profoundly. A hypervelocity star born in the core would begin its journey by blasting directly through the thickest dust and star clouds of the galactic plane. For a significant portion of its initial flight, it would be completely hidden from our optical view, a streaking phantom within the blind spot. We might only detect its presence later, as it finally emerges into clearer skies on the far side of the zone, already thousands of light years from its point of origin and moving on a trajectory that points like a forensic clue back toward the violent heart it fled. Each one we find is a messenger carrying the imprint of a chaotic event we could not witness directly, a silent testament to the explosive forces churning behind the veil. This cosmic shadow falls across the very light of creation itself. Beyond the glow of individual galaxies lies a far more subtle and profound signal, the extragalactic background light. Imagine the combined glow of every star that has ever shone, in every galaxy that has ever existed across the entire history of the universe. That light stretched and faded over billions of years into a diffuse, omnipresent fog of infrared and optical photons is the EBL. It is the universe's total energy budget for starlight, a fossil record of all cosmic star formation woven into a single, faint backdrop, and the zone of avoidance casts a long, dark silhouette upon it. Just as a cloud blocks the sun, the dense dust and stars of our galactic plane absorb and scatter this ancient collective glow, creating a measurable dip in the EBL precisely where we look through the thickest part of the Milky Way. This is not a shadow of a single object, but a shadow of the universe's entire luminous history. For astronomers, this attenuation is not just an obstacle, it is a crucial calibration tool. By meticulously measuring how much the EBL is dimmed within the zone and comparing it to clearer regions of sky, scientists can reverse engineer the properties of the obscuring dust itself. More importantly, it helps them refine their models of the EBL's true, unobstructed intensity. That intensity tells a sweeping story. It reveals the total number of stars ever formed, the timeline of cosmic dawn and high noon, and the efficiency with which galaxies have turned gas into light across the eons. So when we stare into the zone's darkness, we are not just looking at an empty patch, we are studying a precise cutout in the universe's family photo, a missing piece that helps us understand the brightness of everything around it. Our own cosmic blind spot is not a unique flaw in our vision. Every galaxy in the universe has its own zone of avoidance. For a hypothetical astronomer living on a planet within the Andromeda galaxy, the majestic spiral of their own home would paint a thick, obscuring band across their sky, blocking their view of the universe beyond. Their telescopes would point in vain toward the region where our own Milky Way lies, their view completely swallowed by the dust and stars of Andromeda's disk. This is a universal truth of cosmic geography. Wherever you are in the universe, if you are inside a galaxy, your view of the cosmos is fundamentally and permanently biased. You are always looking out from within a forest, and the trees closest to you will always block your view of the distant landscape. This realization reframes our entire search. We are not special victims of an unfortunate alignment. We are simply experiencing the standard condition for any observer embedded within a galaxy. Our struggle to see past our own Milky Way is the same struggle every civilization on every world within every spiral or elliptical galaxy must contend with. Their maps of the cosmos would have different blank spots shaped by the orientation of their own galactic plane, but the principle remains identical. This shared cosmic myopia is humbling. It means that no observer anywhere has a perfectly clear 360-degree view of the universe. Every catalogue of galaxies, every measurement of the cosmic web from any point in the cosmos is incomplete. It is filtered through the dusty lens of their own island universe. Our painstaking efforts to map behind our zone using infrared and radio whispers are not just about filling a gap on our map. They are a test case for the fundamental limits of observation itself, a reminder that the universe always keeps a part of itself hidden, no matter where you call home. The search for hidden galaxies has become a truly collaborative mission. While powerful telescopes gather the data, the monumental task of interpreting it often falls to a global army of dedicated volunteers. Citizen science projects like Galaxy have fundamentally changed how we explore the cosmos, including its most obscure corners. The principle is beautifully simple. Computers are excellent at collecting vast amounts of astronomical images, but the human brain remains uniquely skilled at pattern recognition, especially for the odd, the unusual, and the beautiful. Galaxy presents volunteers with images of galaxies from surveys like Sloan Digital Sky Survey and asks them to answer simple questions about their shapes, features, and any signs of disturbance. This human-powered classification has led to the discovery of entirely new classes of objects, like the rare and mysterious green pea galaxies, but its power extends directly into the zone of avoidance. As surveys push deeper into infrared and radio data, they reveal thousands of faint, reddened smudges on the edge of detection. Are these distant galaxies nearby stars or image artifacts? This is where the crowd excels. Volunteers sift through these challenging images, flagging objects that look particularly promising or strangely distorted. They act as the vital first filter, identifying unusual candidates that warrant precious time on professional telescopes. For instance, a volunteer might spot a galaxy with a peculiar asymmetry or an unexpected jet of material, something an automated algorithm could easily dismiss as noise. That single flag from a person sitting at their home computer can direct an astronomer's attention to a hidden active galactic nucleus or a galaxy in the throes of a violent merger, all lurking behind the Milky Way's dust. This process democratizes discovery, transforming the zone of avoidance from a professional's problem into a shared human puzzle. Every curious person with an internet connection can now help lift the cosmic veil, proving that the quest to map the hidden universe belongs to all of us. The next generation of cosmic explorers is already turning its gaze toward the darkness. Our most powerful new eyes, the James Webb Space Telescope, was designed with the universe's dusty corners in mind. Its immense gold-coated mirror is a perfect collector of infrared light, the very wavelength that slips past galactic dust. But Webb is more than just a bigger version of previous telescopes. It is a time machine tuned to the early universe. When it stares into the zone of avoidance, it is not merely looking for hidden galaxies in our local neighborhood. It is looking for their ancient ancestors. The thick dust of the Milky Way that blocks our view also acts as a natural filter, dimming and reddening the light from everything behind it. For extremely distant galaxies whose light is already stretched into the infrared by the expansion of the universe, this extra reddening from our own dust makes them nearly impossible to detect with previous instruments. Webb's unprecedented sensitivity cuts through this double challenge. It can detect the faint, warm glow of the very first galaxies as they were being assembled, even if they lie in a direction currently labeled a blind spot on our maps. Imagine discovering a bustling ancient city, not in an open desert, but hidden directly behind a nearby mountain range. Webb has the capability to see the mountain for what it is, our own galaxy, and then peer straight through it to the cosmic dawn beyond. Every hidden proto-galaxy it finds will rewrite our understanding of how structure formed in the young universe, proving that the zone of avoidance is not just a barrier to the present, but a curtain over the past. While Webb acts as a powerful magnifying glass on specific deep fields, another revolutionary mission will provide the ultimate wide-angle lens. The upcoming Nancy Grace Roman Space Telescope will perform vast, rapid surveys of the infrared sky. Its core strength is not extreme depth but incredible breadth. Where Webb might spend days staring at a single pinprick of sky behind the zone, Roman will map enormous swaths of it in a single observation. This wide-field approach is perfect for statistical cosmology, for answering questions about the large-scale structure hidden by the Milky Way. Roman surveys will catalog millions of galaxies peeking through the dust, allowing scientists to trace the hidden filaments of the cosmic web, measure the true distribution of mass, and finally understand if the Great Attractor is an isolated anomaly or the tip of a far larger, obscured iceberg. Working in tandem, these two observatories represent a perfect strategy. Webb will provide the exquisite, detailed portraits of individual hidden galaxies, revealing their internal structure and chemistry. Roman will provide the context, the grand map that shows how all those hidden galaxies fit together into the universe's hidden architecture. Together, they will transform the Zone of Avoidance from astronomy's most frustrating blind spot into one of its most fertile frontiers for discovery, a place where the next great cosmic revelations are waiting, veiled only by our own galactic home. The true legacy of this cosmic blind spot may be one of unexpected opportunity. For too long, we have framed the Zone of Avoidance solely as an obstacle, a frustrating barrier to our vision. But a profound shift in perspective reveals something else entirely. This region is not merely a void to be lamented, it is a unique and invaluable laboratory. Because the foreground is so thick and complex, it offers an unparalleled chance to study the very stuff that creates the problem, the interstellar medium of our own Milky Way. Every distant galaxy whose light is extinguished by the dust provides a backlight, a cosmic lamp shining behind a complex screen. By measuring precisely how that light is dimmed, reddened, and scattered at different wavelengths, astronomers can create the most detailed three-dimensional maps of our galaxy's dust clouds, charting their density, composition, and temperature with a precision impossible anywhere else in the sky. It is like using 1,000 distant streetlights to map the exact contours of a single, dense fog bank you are standing within. This is not just about seeing through the fog, it is about understanding the fog itself, molecule by molecule. Furthermore, the extreme environments hidden within the zone, from the violent core around Sagittarius, a star, to the crowded stellar nurseries, serve as natural testbeds for physics under conditions we could never replicate. We can observe how stars form in the densest, most turbulent gas, how black holes influence their surroundings, and how cosmic rays interact with magnetic fields, all within our own galactic backyard, albeit a hidden one. Finally, and perhaps most philosophically, the zone acts as the ultimate cosmic checkpoint for the completeness of our universal senses. It is the one place where we know with absolute certainty that our standard maps are wrong. This known unknown forces humility and innovation. It reminds us that every sweeping statement about the distribution of galaxies or the structure of the cosmos carries a silent caveat until we can account for what lies in the dark. By treating the zone not as a gap but as a frontier, we turn our greatest observational weakness into a source of our deepest understanding, proving that sometimes the most important thing to find is the precise shape of what hides the rest. The ultimate cosmic irony lies in this simple truth. The very object that creates our greatest blind spot is also the one we are most desperate to understand. Our home galaxy, the Milky Way, serves a dual role in this grand cosmic drama. It is both the magnificent subject of our study and the permanent, dusty curtain drawn across our view. Every photon we struggle to capture from behind the Zone of Avoidance has first been filtered through the intricate structure of our own galactic neighborhood. This is not a coincidence of observation, it is a fundamental condition of existence for any civilization born within a galaxy. We are embedded observers, forever looking out from the inside of a beautiful, complex, and obstructive forest. The zone forces a profound humility upon cosmology. It is a permanent reminder that our map of the universe can never be perfectly complete or unbiased. Every measurement, every model of the cosmic web, every calculation of the Hubble constant carries with it a silent asterisk, a note that says our perspective is rooted in one specific, dusty point in space. Our cosmic address is itself the source of our greatest observational challenge. This humility is not a limitation, but a guiding principle. It teaches us to question assumptions, to seek data from every wavelength, and to remember that the universe likely holds symmetries and structures just beyond the veil of our own making. The final lesson of the zone of avoidance is not about what we have found hidden in the dark, but about understanding the nature of the light by which we search. It is a call to keep looking with patience and ingenuity, knowing that the greatest discoveries often begin by acknowledging what we cannot yet see. 25 facts later, the zone of avoidance stands revealed not as an empty void, but as a cosmic crossroads of profound significance. It is a region where hidden galaxies dictate the motion of our own, where dark matter whispers its presence, and where the violent heart of our galaxy churns in shadow. This is no simple blank spot on a map. It is a multifaceted frontier that conceals the architecture of the local universe, shapes the very flows of galaxies, and has, in turn, shaped the course of human ingenuity. Every infrared telescope, every radio survey, every clever gravitational lensing technique was forged in the effort to pierce this single, stubborn veil. As we develop these new ways of seeing, we are engaged in something far greater than filling a gap. We are actively rewriting our understanding of cosmic structure and history, correcting a bias that has been built into astronomy since the first human looked up at the Milky Way's cloudy band. The story of the zone is ultimately a story about perspective. It reminds us that our view of the universe is always and forever filtered through the lens of our own galactic home. The next great discovery is already taking shape in the data from our newest eyes in the sky, waiting for its moment to emerge from the darkness. So stay curious about these hidden corners, for they hold not just answers, but the very questions that will guide us toward a deeper, truer map of everything.